Welcome back everyone to part 3 of our full ANN regression code along. In this lecture, we're going to focus on defining the tabular model. We're going to be able to set up an embedding layer. We'll also set up a dropout function, a normalization function, and then set up a sequential list of layers. Let's get started. All right. So before we get started, I want to point out that there's actually a variety of different types of models you could use on this sort of data set. But we're going to try to give you a tabular model that you're going to be able to easily apply to any data set that looks like the data set we're using here. It has categorical values, it has continuous values. We really want to set up a blueprint or a skeleton of code for you to apply to your own problems, which is why we're using this very kind of specific tabular model setup. So I want to explore first off what was going on with our cat sizes and embedding sizes and our categorical data. So if we were to take a look at some of our cat data, so for example, let's go ahead and just take a slice of our cat's data. So recall, here's our kind of categorical data. What I'm going to do is say cat z as a slice of this. So let's go ahead and say just grab kind of these first couple of values here. So there's our first couple of values. Recall that we actually set up our embedding sizes. So let's go ahead and see what would happen when we pass this into an embedding layer. So if we check out our embedding sizes again, we have 24, 12, 2, 1, 7, 4. So here we have the features that correspond with that, the hours of the day, AM, PM, or the day of the week. And then what happens inside the module, what we're going to end up doing is we say nn.embedding, and we're going to do this for ni, nf, for ni, nf in embedding sizes. So we're essentially going through these tuples. Recall that these are the number of categories, and this is the embedding size. So if you take a look at n in embedding, it takes the number of embeddings and the embedding dimensions, where in our case, that's the number of categories and then the embedding dimensions we set up for it. So this is essentially a list comprehension, and then we pass that into, if we take a look at that result, we get these embeddings. We're going to pass that into nn.module list. And then I'm actually going to say this as self embeds. And this is what we're going to be doing later on inside our model. I'm just kind of breaking it down for you so it's not that confusing when you see us set up our tabular model. But now I can see this module list of these embedding layers. One for the 24 hours, one for AM, PM, and then one for the weekdays. And what we can do then is inside the forward method, what we're going to have here, and I'll say embedding z is equal to an empty list. We say for I, e in enumerate, that self embeds list that we just created. We'll take embedding z and append, and what we're going to do here is grab that embedding. Recall that's that embedding layer right there, and then we're going to pass in our data into it. So let's go ahead and say pass in that single row of data. So recall cats with a z, that's kind of that little subset of data. In fact, we can make it even smaller if you want. So there's just kind of 2 rows, so we can explore just 2 rows. So we run that, and this is the exact method we're going to be using in our forward method, but we'll be using it on all the data with cats, with an S, but here we're using it on this little subset. And so now let's actually take a look at the result of embeddings z, and here we can see the result after we actually go forward through it. We end up getting these tensors here with the embeddings. And note their lengths here. We have 24 items in this first tensor. We have 2 items in the second tensor and 7 items in this third tensor. Those are the actual embeddings. It's now giving values to those one-hot encodings that we did when we set up that embedding table. Okay, and essentially the next part of that, we set up z as the output, so we say torch cat on embedding z, and we're concatenating it along dimension 1, And this is what we're doing in the forward loop. So then we get this tensor that looks like this. Everything's concatenated together. And then after that, we'll go ahead and then pass it through a dropout layer. So we'll say something like self embedding drop. We create a dropout layer. And what a dropout layer does is during training, it's going to randomly zero some of the elements of the input tensor with some sort of probability that you provide. So you can, by default, it's 50% probability. But what this does is essentially randomly turns off 40% of the neurons. And that way, you don't overfit. It's a really common strategy. And then what we can do is say z is equal to self embed drop, and pass in the z from before, and then we get back this tensor. So this is how the categorical embeddings are being passed through the layers. So this is what we're going to see in our forward method. This is just me breaking it down step by step. So that we don't see it for the very first time in all this weird jumbled code in tabular model. But I just want to explain one more time what we're actually doing. Recall, right now we have this embedding sizes list of tuples, where we have the number of categories and then our size of embeddings. And the size or dimensions of these embeddings were based off this rule that will max out at 50, and the rule of thumb will be, we'll say, divided by 2 of that size. So that's why we get 2412, 21, and then 74. And we use these forward slashes here again because we want to make sure these are integers. You can't have a 4.5 shape on an array. And then we took a little subsample of our categories. So we have this little tensor, essentially just the first 2 rows of data. And what we ended up doing is in our forward method, we're going to build out this kind of list of embedding layers where each embedding layer corresponds to one of the categories, 24 hours in a day, AM or PM, 7 days in a week. And then during the forward method, what actually happens is we end up applying values to each of those one-hot encodings until eventually we start putting a lot of strength to maybe hour number 12 in a day because that's lunchtime, or PM because it's night and rides are going to be more expensive during night, or maybe the last 2 of the weekdays like Saturday and Sunday, or the weekends, etc. So we're actually then assigning numerical values to those one-hot encodings that we created through the embeddings. And then we stick them all together into one tensor so that it's not just kind of 3 tensors here. So you'll see that occur as well. And then we're going to end up passing that through a dropout layer until we kind of start getting assigned values. So that's all we're going to be doing to deal with these categorical values in our tabular model. So I just wanted to break it down step by step so you didn't see it for the first time within that class. So let's go ahead and build out that class now. We'll say class tabular model, and we inherit from nn.module, just as we did before. We'll have 2 methods, our init method. Right now I'll just put in pass here, as well as our forward method. We'll say self, and right now that will also be pass. So what are we actually going to take in to our instantiation method? Well, we need to take in some information on the embedding sizes. We also want to take the number of continuous features. We'll also want an output size, the number of layers being used, and finally the probability. We'll default it to, let's say, 0.5, but that's the probability for the dropout layer. And let's make that equals. Okay, so we don't need that pass anymore since we're actually going to do it. We'll go ahead and instantiate the inherited class with this super command that we did last time. And then we set up self embeds is equal to, and I'm just going to use the exact same code I showed above. Whoops, let's make sure that's embeds. So this exact same code I showed above here, where we had this little NN module list. So I'm doing the exact same thing that we just went through. And really take your time with the lecture notebook in case you were a little fuzzy on that. I want to point out that the lecture notebook, if you kind of scroll up to where we have kind of a written explanation of everything that's going on within that tabular model. It's a really complex model, but then it's really flexible to any data set, which is why we choose it. All right, so let's go ahead and continue on to the tabular model. We set up those embeds, or those embeddings. We say self emb drop. It's going to be equal to that dropout layer. We'll go ahead and have you be able to edit the probability of dropout, something you can play around with. Often 50% is a pretty good number to start with. And then the last thing we're also going to do is we want to normalize that continuous data to make sure it all falls within the same magnitude. the order of magnitude range. And we can do this by simply saying batch norm 1D on n continuous. And then I'm going to create a variable called layer list, where then I can store my layers. And the number of embeddings is going to be equal to, or if you recall, we have NF here, which is that embedding size, and I want kind of that total number, so I want to sum it up. So we'll say the following. We'll say go ahead and say NF for NI NF in embedding sizes. So that's going to be a list comprehension, essentially just to grab a list of those NF values, and then I want the sum of those. So essentially, if we look back at what this is for NI and F in embedding sizes, all I wanted to do was to grab the sum of these second numbers, 12, 1, and 4. Okay, so that's going to be the number of total embeddings there, and then N in will equal to the number of embeddings, NEMBS, or let's just say number of embeddings so it matches the lecture notes without an S, plus n continuous, which is, again, defined when we actually create our tabular model. All right, so we have that ready to go. And now what we're going to do is inside of this, we can set up our layers. So we'll say for I in layers, and here you can get to define how many layers you want. But essentially, every layer will be the following. We'll say, go ahead and create a linear layer with n in and I. And then grabbing that layer list again, go ahead and append a rectified linear unit activation. We'll say in place is equal to true here. And then we'll say, again, another layer list, append that normalization process on I, grab that layer list, and then finally let's go ahead and append a dropout with some probability, and then we'll say n in is equal to I. And then outside of this for loop, we'll say layer list will have some final layer at the very end. So this linear layer is going to be equal to layers minus 1, that very last value inside of layers, by output size. And in this case, the output size should just be 1 since it's a regression problem. We're just predicting a single value. And then we'll say self.layers is equal to nn. In order to make this all work, we'll say sequential here, asterisk or asterisk layer list. Okay, so what we're doing here is then this allows the user to define how many layers you want. And then for kind of whatever number they decide for I in layers, we can then. So here's what's really awesome about setting up this for loop in this manner. This basically allows flexibility for you to define your network based off this layers parameter. This layers parameter, what it's going to look like is essentially a list. You're going to end up passing layers is equal to, and as a list, you get to define, okay, I want 200 neurons on my first layer, then 100 neurons on my second one, and then maybe 50. And this allows you to play around with these values. So it's super flexible, which is why we decided on this sort of tabular model. Again, we have the embedding sizes, number of continuous, the output size, layers, and then probability for that dropout layer. And this layers is where you get to really play around with it. And as I keep mentioning, in our lecture notebook, I'd highly recommend that you scroll up and kind of read through this walkthrough. It explains everything that we've done so far. Okay, the last thing we want to do is set up our forward method for our tabular model. So let's go ahead and do that and finish this up. So we have our forward model. All we need to do here is first pass in the categorical features and then the continuous ones. Embeddings will start off as an empty placeholder list, and then we'll say for IE and enumerate self embeds. Remember, that's an attribute we defined earlier. We'll say embeddings dot append, and we'll append off that actual embedding function xcat :I. Remember, that's exactly what we just did when we were kind of walking through the steps in the forward method. So all I'm doing here is just generalizing it. and then we'll say torch cat on embeddings 1, and then say x is equal to self dot. And if you want, you don't have to keep calling it x, but it's kind of easier to keep track of everything if you just keep using the same variable. And then we'll say x continuous is equal to self bn continuous, passing in those continuous features. Then we'll go ahead and say x is equal to torch cat, where we take in x from the categorical, and then x from the continuous, along axis equal to 1, and then we'll say x is equal to self dot layers on x, return x. And what this is doing, this part is essentially what we just showed you up here. We kind of walk through that entire thing in the forward method. So we're doing the same sort of appending on this embeddings, we're doing that same categorical, and all this is doing is, at the end of the day, we kind of want to stick this all together to one tensor that's going to be able to have values for those one hot encodings of those categories. So that's what this category part is doing, and then we combine it with the continuous ones in here, because x right here, this is for x categories, because here we're dealing with the embeddings. So we combine them here in this line. And then finally we have kind of the output of all those layers. All right, so I know there's a lot to go through here, but I would highly recommend just really taking your time to understand this tabular model and what it's doing, and read our lecture notebook. That's what it's there for. It's there to help you understand what each of these lines is doing. But now you have a tabular model that you should be able to easily define, and it's going to be flexible enough to work with any data set that you encounter in the real world. Coming up next, we're going to actually define a loss function optimizer for this model, perform our train test splits, and then train the model. I'll see you there.